Section 5.7, Systems of Linear Inequalities. We're kind of going to be building on the first half of Chapter 5 and Section 5.6. We're going to be basically combining those two broad topics into one condensed section in Section 7. So a system of linear inequalities, it's a vocabulary term. It's two or more linear inequalities in the same variables. Basically, it looks like this. Y is less than x plus 2, and y is greater than or equal to 2x minus 1. That would be an example of a system of linear inequalities. Basically, it's two of what we did in section 6 on the same graph, or the same coordinate plane. Okay, so a solution, it's an ordered pair, again in the form xy, that is a solution of each inequality of a system. So in our examples here where it says tell whether the given ordered pair is a solution to the system of inequalities, what we need to do is we need to check this ordered pair into both of these inequalities. Okay, if it's going to be a solution, it has to satisfy each inequality. It has to satisfy both, or all three, or all four, or however many there are in the system. It's got to be a solution for all of them. If it doesn't work for one, it's not a solution to the system. Okay, so we need to check both of these inequalities. So let's just jump right in. We'll start with the first one. So we're going to have my y value is 5. And we're going to see if that's less than 2 times my x value, which is 3. So we got 5 less than 6. That one checks out. Okay, so we'll do the first one here in red. Second one we'll do in blue. Okay, so again, take your y value, 5. We're going to see if that's greater than or equal to your x value of 3 plus 1. 3 plus 1 obviously is 4. 5 is greater than 4, so that one checks out as well. So the ordered pair 3, 5, the question's asking, tell whether the given ordered pair is a solution. If it checks out for both, it is a solution. Okay, yes, it is a solution. 3, 5 is a solution to the linear system of inequalities. Okay, let's go ahead and check number 2. Different ordered pair, negative 2, 0, but it's the same system. Y is less than 2x, y is greater than x plus 1. So we'll start with the first one, the one in red. Y is less than 2x. So my y value is 0, less than 2 times my x value, which is negative 2. So 0 is less than 2 times negative 2 is negative 4. Now the question becomes, is 0 less than negative 4? The answer to that, obviously, is no, not a true statement. If you get to this point where the first one does not check out, you don't need to check the second one. Because remember, the definition of solution has to satisfy each of them, all of them. If it doesn't satisfy the first one, it doesn't matter if it satisfies the second one. It's got to satisfy all of them. So if you get to this point where the first one doesn't work, you don't need to check the second one. If the first one does work like it did in number 1, then you need to move on to the next one. Okay, but if it doesn't work for the first inequality, or for any inequality that you test, you don't need to keep testing, because the answer is going to be automatically not a solution. Okay, not a solution. If it doesn't work for one of them, it's not a solution to the entire system. Okay, so just a little basic info on what a solution is. It's really no different than what we did in section 6 or section 1, or any section with systems. It's got to satisfy both. Okay, but the main topic in this section builds off the main idea in section 6 of graphing linear inequalities. But now we're going to be graphing systems of inequalities. Okay, so step number 1, graph each inequality in the same plane. And then step number 2, find the intersection of the shaded areas. The solution, or the solution area, is the common shaded area. I'm actually going to show you 2 different ways to find the intersection of the shaded area. One way is a little more brute force. The other one you can kind of say is a little less messy. Okay, so number 1, graph the system. Let's give this a shot. So I'm going to go ahead and bring in some graph paper here. We got y is greater than 2x minus 3, and y is greater than 1/2 x plus 1. So I'm going to go ahead and bring in my x and y axis. There's our coordinate plane. I'll do the first one, the first inequality in red. I'll do the second one in blue. Okay, so the red one, y is greater than 2x minus 3. So it's in slope-intercept form already. So we started our y-intercept of negative 3. Our slope is 2, which means we go up 2 into the right 1. So our next point is going to be right there. And then we're going to keep that pattern. Up 2, right 1. Ooh, let's try that again. Let's get rid of that point and try it again. Up 2, right 1. Not much better. Up 2, right 1. Up 2, right 1. And we could keep going, but we don't need to keep going off the graph. Instead of going up and to the right, we could also go down and to the left, and I've really only got room for the 1 point right there. Okay, so we need to figure out solid line or dashed line. This is an or, it's not or equal to, it's strictly greater than, which means it's going to be a dashed line. So let's go ahead and draw in our dashed line there. Put the arrows there. Now we need to figure out where to shade. So it's either going to be the 0, 0 side or the non-0, 0 side. If we plug in 0, 0, so I'll do this off to the side. So we got 0 is greater than 2 times 0 minus 3. So I get 0 is greater than 2 times 0 is 0 minus 3. 0 minus 3 is negative 3. This is a true statement. 0 is greater than negative 3, which means we're going to shade this area. Pardon me for the coughing. That would be one of my sons here sitting with me while I'm making this video. All right, so let's move on to the blue line. Y is greater than 1/2 x plus 1. Again, this is slope-intercept form, so we started our y-intercept of 1. We'll use our slope of 1/2 to go up 1 and to the right 2. So we make a mark at 1. We go up 1 and right 2. Keep going, up 1, right 2, up 1, right 2. Instead of up and to the right, we could also go down and to the left, down and to the left, down and to the left. This line is going to be a solid line because we have the or equal to part here. Okay, so let's put in the solid line. And now we need to figure out which side of the line we need to shade. So if we plug in 0, 0 again, because 0, 0 is not on the graph, that's a great thing. So we'll have a y value of 0 greater than or equal to 1/2 times my x value of 0 plus 1. 1/2 times 0 is 0, so I'm just left with 1 on the right-hand side. 0 greater than 1. That's also a false statement, or it is a false statement. The first one was true. So I tested the 0, 0 side and got a false statement, which means I'm going to shade the opposite side of the line. So that's going to be this half up here. Let me scroll back to the graph here. Our final solution for the blue one is right over here. And I guess it would go on the entire side of the line. Now, the solution area is the common shaded area. So where do the two shaded areas overlap? Well, obviously we can see, or I hope you can see, that it is this area right in here. This is our final shaded area. Like I said, this method I'm showing you right now is a little messy. It's more like what I said, brute force. It's kind of tough to determine what's what. I'm going to show you here in the next example maybe a little cleaner way to do things so it doesn't look so scrambled and so messy. You might need, with this method, you probably need 2 different colors. At least 2 colors. A third would be better. You know, like I've got blue, I've got red, and then I've got purple. That's really the only way to see it. I guess if you're using just pencil, I would shade lightly going this way, shade lightly going this way, and then you can kind of see the darker area where the 2 pencil shadings overlap. That would be the solution area. For long-term sake, though, I only need the final solution area. I don't need the extra, you know, the non, where it works for one, like down here or up here, but not the other. I just really need the final solution area. Okay, so let me show you one how to do that real quick. Number 2 here. Let's go with y is less than or equal to 3, and we'll have y is greater than x plus 2. Okay, so again, I'll do the first one in red, I'll do the second one in blue. I need to bring in a coordinate plane here. So let me draw that in. There's our coordinate plane. So the line y is less than or equal to 3. That's a horizontal line because the number in front of x, well, there isn't an x, so that would be 0, which means a slope of 0. And then our number here, 3, that's our y-intercept. So we're going to have a horizontal line through a y value. Ooh, let me try that again. A y value, horizontal line through the y value of 3. Okay. Now, the sleek way, or the faster way, the less messy way to graph these inequalities. Let's figure out which side of the line we need to shade. So if we plug in 0, so if we get 0 is less than 3, 0 is less than 3, that's a true statement, okay? So what that means is I tested down here, the 0, 0 side, and I got a true statement, which means I need to shade that side of the line. So what I'm going to do, I'm just going to draw teeny tiny arrows off the side of my line saying this is the side I'm going to shade when it's all said and done, or if I were to just say shade or just have the one line in my graph. So that would be the bottom side of the line. That's the area that satisfies the red one. Okay, do the same thing for the blue one. Your y-intercept is 2. This is slope-intercept form. Your slope is 1, so that's up 1, right 1. And we just need to continue that pattern. So we're going to keep going up one, right one, up one, right one, up one, right one, or down one, left one, down one, left one, down one, left one, down one, left one, all the way down. That's good enough. Since we have a strictly greater than, that's going to be a dashed line. So we're going to put a dashed line on our graph here. Okay, then we need to figure out where to shade. So we'll plug in 0, 0 because 0, 0 is not on the line. That's a great thing. So plug in 0, 0. So we'll have 0 greater than 0 plus 2, which is really just 2. Is 0 greater than 2? No, it's not. That's a false statement. So we tested down here. We got a false statement. So that's this side of the line. It's going to give us all false, which means the correct side, the true side, is the, I guess you'd call it upper left-hand side. So that's this direction up in here. Okay, so I just draw my little arrows off that line. Now the question becomes, where do the arrows point at each other? Because, you know, if we're looking for the common shaded area, for the red one, we're down here. The blue one, we're up here. The common shaded area is right in here. It's where the two sets of arrows are pointing at each other. And this would be your final answer, that little triangle area, that would be your solution area. That's the area, those are the ordered pairs in that purple shaded area that would give you true statements for both the red one and the blue one. So if it satisfies both, remember going back to the definition of solution, that is where our solutions for the system are at. Okay, let's go ahead and try one more. So we'll do, this is number 3. We're going to go with y is greater than or equal to negative x plus 4, and we're going to have x plus y is less than or equal to 0. All right, so the red one, the top one, we can do in red. That's fine. That one is already in slope-intercept form. The bottom one is not in slope-intercept form. So let's get it in slope-intercept form first. We'll do that by subtracting x. So we'll have y is less than or equal to, well, that's just negative x. And if you want to put plus 0, you can do that too. It's up to you. Okay, so now we've got them in slope-intercept form, the red one and the blue one. So let me bring in my xy plane one more time here. Kind of a crooked y-axis. Let's try drawing that in again a little better. And then our x-axis is right there. So the red ones, y is greater than negative x plus 4. We start with our y-intercept of 4. That is right here, y-intercept of 4. Slope is negative 1, so that's down 1, right 1, negative over positive, down 1, right 1, negative over positive, negative over positive, negative over positive. You can keep going. I'll just put a couple more points on the graph. Instead of going down and to the right, remember you could also go up and to the left, okay? This is going to be a solid line because we have that or equal to part. Whoops, let me get rid of that. There's our solid line through our points, close enough. Okay, then we need to figure out, let's try drawing that arrow a little better. There we go. Okay, so let's figure out which side of the line we need to shade. So if I plug in 0, 0, because remember 0 is not on the graph, so we can use it. So we'll have 0 is greater than the opposite of 0 plus 4. The opposite of 0 is still 0, so we're left with 0 is greater than 4. That's a false statement. So that means I tested here, got a false statement, which means I shade opposite of that. So that's up this direction. Okay, so my shaded area for the red one is up and to the right. Now we need to do the blue one. So y is less than negative x plus 0. So my plus 0 is my y-intercept. That would be the origin, 0, 0. So right away I know I can't use 0, 0 when I test my inequality. So I'll have to pick a different point. So we'll figure that out in just 1 second. So my slope, just like the red one, negative 1. So which means these lines are going to be parallel. Okay, so as a little side note, so we're going to go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. They have the same slope. They're both negative 1, so that means the two lines are parallel. So we'll just keep putting our points on the graph here. So we got there, we got there, we got there. Okay, this is also a solid line because it's got the or equal to part as well. So that's going to be solid through the blue ones. So now we can't use 0, 0, but we could use like 1, 0. Okay, you don't need to pick something way out here. That would just be a lot of extra work, see? Okay, so we don't need to go all the way out there. I'm just going to use 1, 0. So this, let's see, so I'm going to just 1, 0. I'm just going to write that ordered pair there. So my y value is 0, less than or equal to the opposite of 1 plus 0. Let's see, plus 0 is not going to affect anything. The opposite of 1 is negative 1. Is 0 less than -1. The answer there is no. That's a false statement as well. So I tested the right side or the upper right side of the line and got a false statement on the blue one. Okay, so when I get a false statement on the upper right hand side, that means my shaded area is the lower left. Now, do the shaded areas cross? Well, my red one goes up and to the right. My blue one goes down and to the left. My shaded areas do not cross. If your shaded areas do not cross, your answer then is no solution. There's no common shaded area. There's no place where those two shaded areas are going to cross. So there's no way you're going to have a solution. So your answer for this one is no solution. It is possible for a system to not have a solution, and this would be an example of what it looks like. The lines probably have to, well, they wouldn't have to be, not probably, they do have to be parallel, and then the shaded areas have to be going away from each other. So there is a possibility that you could have no solution. It's pretty rare, but it does occasionally happen.